Why did people drill the Kola super deep borehole and extract core samples from there? Because that's the only way to unambiguously tie what happens at depth to actual data. The deeper we go, the more expensive this whole endeavor becomes. The price of a core sample increases almost geometrically.
By the time this is analyzed, it's likely post-mortem data, since a decision has already been made. The specialized equipment we manufacture is perfectly suited for this task. Why? Because our equipment is highly low maintenance and can reliably operate in conditions close to extreme: high temperatures, heavy dust, and moisture. In relative units, even if we see iron in our physical measurements in impulses per second, we can still provide, for each element, copper, zinc, lead, and iron in percentage terms in relative values. So here we have real-time information.
And information means money and speed of decision making. Hello! Well, you may have already seen me. My name is Alexander, and now I'm no longer the director. Well, in this podcast, I'm no longer the director of science. In this podcast, I'm a professional researcher with a background in geophysics, who has traveled extensively to oil and gas production sites, witnessed a vast array of operational challenges, and has gained hands-on experience with both drilling cuttings and core samples. So, a little bit, I can tell you about this very pressing and currently relevant topic. For those watching this video simply because two serious young men are talking, well, that's always interesting. Drilling cuttings are something that inevitably form during drilling operations. For now, we're speaking in very general terms. A huge drill bores into the Earth's crust, and all that earth has to go somewhere. All of it gets washed up to the surface. All these little pieces and fragments are called cuttings. And in the past, cuttings were basically considered waste, a byproduct that no one was particularly interested in. Let's discuss it that way. And core samples are something that some people still practically worship. A core is a cylindrical piece of rock extracted from a borehole. Cuttings are essentially free and are produced during drilling no matter what. It's simply impossible to have drilling without producing cuttings. Core sampling, on the other hand, is an incredibly costly and resource-intensive undertaking. To obtain a core, that solid piece of ore from the depth we're working at, you have to completely halt the entire drilling process, pull out everything, absolutely everything that's in the well, removing every single component from the shaft, then attach a special cylindrical bit to the drill, lower it all back down very carefully so as not to damage or crack anything, and, well, successfully extract a perfectly representative sample piece of rock. Drill through, remove this sludge, and extract it. Very carefully extract the equipment from the hole, then carefully reassemble the whole setup and continue drilling. Naturally, the deeper we go, the more expensive all of this is inevitably going to become. And on top of that, the price of the core increases exponentially. When we're talking about this kind of drilling, it's always, at best, in hard-to-reach places. And in harsh reality, sometimes it's easier to get to the ISS than to the places where these valiant drillers are working. And to the cost of drilling itself, we also have to add the cost of logistics. In general, drilling as such is an extremely expensive process, and extracting the core makes it even more costly. And another thing is that once we've retrieved the core, it needs to be studied very carefully and in detail. There are also all sorts of storage requirements for it. For example, at our university, the Institute of Geology and Mineralogy had an entire hangar dedicated to core storage. And students did their internships there. There was so much core that everyone had described it at least once. It provides a huge amount of information. In other words, we could never do without core samples. But it provides this information slowly, because there's no way we can collect core samples from the entire well. It would just cost such astronomical amounts of money that there wouldn't be enough oil extracted to cover the cost. And so the question arose. If this is such an expensive undertaking, then why not make it? Well, we can't make it any cheaper. But why not make it more efficient? And that's when the attention of the progressive community turned to drill cuttings, which used to be considered just waste. The crushed rock would just lie next to the well, and someone would be told to take it farther away so it wouldn't get in the way. But in fact, it's the very same rock that we're drilling through. When with not much effort, we can correlate it, the cuttings that are brought to the surface from the depth where we are currently drilling. And after all, it's the same rock, just not in the form of a cylinder, but as crushed stone. And from that we can extract a pretty decent amount of information. And information means money and faster decision making. Because geophysics, as a method for deep study of the Earth, is very good. I really love geophysics. But this is solving an inverse problem, and it's impossible to interpret geophysical data unambiguously. So, for example, we conduct detailed seismic surveys, and based on those results, we can accurately predict that at a certain depth we have one type of rock, then there will be another type of rock, and then we will reach our target reservoir. And finally, we are very happy. So we've reached the reservoir, and now we're going to start pumping oil. We start drilling, and then something goes wrong. To figure out what's going wrong, well, we have to extract a core sample. But this pause is very expensive and time-consuming. But if we're drilling, something goes wrong, and we have cuttings as a source of information, we immediately understand that we have problems that we can fix right away.
Here's a question right away. So cuttings, okay, an inline analyzer is complicated, but let's say, I don't know, a portable analyzer or a laboratory one that's portable. You take a sample, prepare it, put it into the lab analyzer. Is this kind of practice already in use?
Back when I was first beginning my professional career in this field, the highly respected and well-regarded company known as Thermo Fisher Scientific actually offered such highly specialized and technical solutions for lifting, well, that is for cuttings. They didn't lift it, they worked with what was already on the surface. There was a special oven, a special machine for cleaning the cuttings, drying them, and bonding them into specially prepared epoxy pellets. And then automatically sending them to a microscope that costs about as much as an oil well. So yes, such a solution existed because the information ultimately paid for itself. But there are 2 points to consider here right away. First, an electron microscope is an electron microscope. It's an incredibly expensive and highly sophisticated, exceptionally finicky and delicate piece of equipment. Second, even with all the power of Thermo Fisher, the entire workflow involved here was, well, you can't really call it fully online. It was almost there, but still not quite fully integrated. This is one of those cases where my favorite phrase, using a microscope to hammer in nails, has never sounded more appropriate. I mean, why use a microscope that costs millions of dollars when a much simpler, more elegant, and already well-established solution like inline X-ray fluorescence analysis exists and is ready to go? Of course, there are some nuances as well. For example, with this type of microscopy and such sample preparation, we can definitively identify the rock types we're penetrating. But X-ray fluorescence only gives us the elemental composition, just an elemental analysis. We already have geophysical data.
Better than nothing.
Yes, so we already have geophysical data. Inevitably, we have it. Well, because drilling without geophysics is, well, that's just not done. So we have a general idea of the rock's electrical conductivity at a certain depth, or its acoustic rigidity, or its radioactivity. We can see what elements it consists of because the cuttings have been brought up. And we've done XRF analysis on them, and you don't need to be a pioneer in this field for that. So that a knowledgeable person can connect all this data into a single picture, and still acquire all the same information that would be provided by either microscopic analysis or, well, not all of it of course, but a significant portion of the information that core analysis would provide to us.
Neutron gamma logging is also widely used. When a neutron generator is lowered down into the well, but again, we need to retrieve it, lower it down.
That's the first point. First of all, yes, we have to insert something down to the depth, analyze it, and then retrieve all this equipment. This analyzer here. And the second point is that the data we obtain is not about the chemical composition, not about the petrological composition, so to speak. The place where we are now, where we are drilling, when we conduct such logging, such analysis, we do not find out what kind of rock it is. What we learn is the conductivity or the acoustic rigidity of the rock at this location. Two different types of rock can easily have the same physical parameters. If not one, then the other. And here, in order to clearly distinguish between them, we either need to conduct such an exploration that combines all the methods, gamma logging, acoustic logging, electrical logging, basically perform all types of logging, which is time-consuming and expensive. And why duplicate what we've already done, most likely? Or we can take the information we already have, the a priori data, and use it more effectively. In other words, to solve the geophysical problem unambiguously, all we're missing is literally seeing what has come up to us from above.
The chemical composition.
Well, at the very least, yes. Ideally, of course, it's core samples, which give us the rock formations as they are actually laid down there. With those, we can immediately find out a whole lot more. Core samples are really the ideal. I mean, well, that's why people drilled the Kola super deep borehole and brought up core samples from there. Because, well, it's the only way to be absolutely certain about what's happening at depth. But even with the best possible analysis of drill cuttings, it's not the same as core samples. We will never be able to get rid of that difference. So people who specialize in this can rest assured. But when we get data from seismic surveys, well, from geological or geophysical exploration, we can interpret it in one way or another. For example, let's take electrical prospecting, which I still remember at least something about. So we've conducted an electrical survey, and I'm trying to construct a cross-section based on this data, and I can easily build two models that will fit the data I obtained at the surface. Either I have a layer like this with a certain conductivity, and then another layer of a certain thickness with a different conductivity. Then a small one with another conductivity, and a very thin one with a third. Or the other way around. One here, then another one there. You can build as many models as you want. And until I actually see what's inside, I can't choose the exact model. And the drilling cuttings will help me with my model. They immediately allow me to refine and understand what's happening. Literally in real time, my cross-section becomes more and more accurate. My model becomes increasingly relevant and matches the real data. And if something goes wrong, first of all, I can realize that something has gone wrong and immediately understand it. And secondly, I can make adjustments. Or, well, I have two options for how the cross-section might look. And in order to understand what exactly is wrong with it, I need to see the rock that is at a certain depth where the problems begin. Well, I need to see it. Or at least do something with it, but it has to be at the surface. And if I rely only on the core sample, then I reach the problematic section where the questions start to arise. I stopped the drilling process, pulled out the drill, lowered another drill and extracted the core sample. Took it out and analyzed it. And only then, that's it, I made a decision. But with the cuttings it's like, well, the drilling is ongoing. We've reached the point where questions start to arise. Well, the cuttings are already sort of on their way to us and now we're about to have them. We took it out and analyzed it. Maybe there was just a tiny bit missing, some kind of hint or some parameter. With the cuttings, we figured it out right away, made a decision, and steered the drill to one side or the other. And kept going.
Well, I mean, as I understand it, we also can't just core to analyze everything immediately and quickly. There are still some time delays. Yes, by analogy, much like how a laboratory analysis is performed. But here, we can actually obtain data from the drill cuttings in real time. Every 3 minutes we can see the elemental composition.
At the very least, that is certainly one aspect of it. The simple fact of the matter is you have spent millions upon millions of dollars just to get this unremarkable little cylinder from such a great depth. So naturally you're going to treat it with the utmost care. That means you'll prepare it properly. You'll analyze it in a specially equipped laboratory and obtain all the information. In fact, the core analysis industry is quite substantial as well. There are companies that produce only core analyzers, and they do it well, but of course the prices match. So yes, there is a delay. And in addition, there's a chance of making a mistake. Messing up the core is a real possibility. And nobody wants to be the person who ruined the core. That's also a psychological factor. Of course, it provides a lot of information, but it gives it much later, afterwards. But of course, that's better than nothing at all. But these are losses one way or another. But when we're working in a live, real-time environment, every few minutes we carefully plot data points on the profile of our well to fully understand exactly what's happening and make informed strategic decisions. We act correctly, and we act very quickly.
In other words, it means deciding quickly, because once the core is analyzed, it's already post-mortem data. By then, decisions are likely already made, and things have been carried on anyway, the work. They're not going to wait, of course, for several hours or even days while the core is being analyzed. Yes, so here we have operational information. Maybe it's not as precise, not as reliable.
Well, yes, we have pieces of rock, and as they are brought up to the surface with the drilling fluid, they all get mixed together. So we won't be able to see exactly in what order, or which rocks are lying there, or how everything is precisely arranged in detail. We won't be able to create a super detailed cross-section, but in general, we still get a huge amount of very useful information that allows us to, well, at the very least, look, we assume that at a certain depth, we need cores of a certain quality. Well, that's always part of the plan anyway. There's no way around that, but analyzing the cuttings shows that in this spot, a core sample isn't necessary. Everything here is just as expected by the book. Wonderful.
On the contrary.
Yes.
First we see something.
Is off.
It is really worth it.
Yes, so either we save ourselves a lot of money and time because we didn't take a core sample where it wasn't really necessary, it wouldn't give us anything at all, and that's already a saving. Once we've saved, twice we've saved, or on the contrary, we realize that our practice doesn't fit at all with the theory developed by the wise geophysicists. let's stop and take a look and make a decision. That is, this allows us to take samples not at regular intervals or as prescribed, but when it's actually needed.
Yes, it's a very interesting task. It's especially interesting for us because the specialized equipment we produce is ideally suited for this task. Why is that? It's because our equipment is designed for low maintenance operation. It is capable of operating in environmental conditions that are, let's say, close to being extreme, high temperatures, dust, moisture, and vibration. That is the first point. Secondly, in fact, it is quite compact, which means that its dimensions are small enough so that we can easily install our analyzer. To be more precise, it's about 1.5 by 2 meters. So, considering the fact that we are working out here in the field, this is likely quite important for us to keep in mind as well. And really, there are no major difficulties or problems to encounter at all. You can easily get results on the full chemical composition every 2 to 3 minutes without any significant delay. Taking this into account even, I think I admit that there might be some margin of error when compared to standard chemical analysis. But all other things being equal, even in relative units, if we see, for example, iron in our physical measurements, measured in impulses per second, we can still provide the specific relative percentage for each element. Copper, zinc, lead, iron, they are almost always present everywhere. So in relative units, has it become a certain percentage higher or lower? That is, even without tying it to a description.
Even this qualitative analysis, more or less, is incomparably better than having no analysis at all. Now, let's imagine that we completely forget about numbers. The device just tells us either low or high. And so, we're drilling through limestone. That means there will be a lot of calcium, and the device says, a lot of calcium, a lot of calcium, a lot of calcium. And then suddenly, we've drilled through and reached some kind of bedrock, granite for example. That's it, the device says, guys, the calcium is gone. Or maybe there's just a little calcium, because it doesn't know what gone means, it's not calibrated. And basically it works so simply that it just points a finger up or down. Even this
indicator.
Yes. And even because of this, whether it's okay or not okay, we come to the point where our section is either confirmed or not confirmed. And, well, how much is the process going the way we expect it to go? Are any urgent measures needed?
From this point of view, indeed, it can probably be a very effective tool. Everything we have from calcium to uranium, yes. And if we have these elements, let's say conditionally, yes, this also varies from element to element. If it's more than 1.1%, yes, all of this will be very clearly visible in the spectrum. It will be very well identified. All metals are wonderfully detected by X-ray and can be determined as a percentage. This specific information can be provided very accurately and effectively used throughout the entire work process. Once again, I must say that this situation upsets me quite a little bit. The simple fact of the matter is that our major oil companies, yes, are finally starting to experiment with detailed sludge analysis. But they simply don't know about our existence yet, yes, so they come in. These are companies that are only just starting out in this particular field. And the various solutions I see today, they are probably quite good as well and may certainly have their place in the future. But this is a slightly different direction, and this new solution still needs to be developed. Whereas we already have a solution that has been refined over many years and tested at large enterprises, which our equipment is designed to operate around the clock 24/7, 365 days a year, and can work in harsh industrial shop conditions. But unfortunately, the people and businesses who truly need this specialized equipment are often completely unaware that we even exist. That is why the specific idea to start recording this podcast first came about, because I can see that this significant need is steadily emerging and growing in the market today. I fully understand and appreciate that customers have a significant number of lingering doubts about this, that it is probably quite difficult and complex to simulate effectively somewhere in a laboratory or to physically bring in several large barrels of sludge. It's the same with pulp. Here we find ourselves in a somewhat more complicated and problematic situation compared to ore, which at least can be transported. Nevertheless, I am confident that this topic will continue to develop. Progress does not stand still. There have already been the first prerequisites and the initial promising signs in this direction, coming from both major mining and global oil companies.
Here, I would even like to share a bit of my own experience. When I was a bit younger and much more reckless, our company was promoting a new approach to analysis. Core, not cuttings, the so-called digital core analysis. It was a kind of feature at the intersection of very advanced technologies and truly breakthrough software, which made it possible to extract much more information from the core than it ever could provide before. The topic was indeed very pressing and urgent. Wherever I turned, I encountered a fair bit of confusion and skepticism from the more straightforward folks working on the ground. They would say things like, well, that is great and it sounds wonderful. But why exactly do we need it? And just how much is it going to cost us? Thank you for your attention. Here's the coffee, and there's the door. But as I mentioned, I was reckless. And I followed the news in the oil industry very closely. At that time, everywhere you turned, people were talking about the Bazhenov Formation. You know, those are the oil reservoirs of the Bazhenov Formation, which have very rich deposits, but they have very low permeability. So in other words, there's a lot of oil, but it's very hard to extract. And accordingly, you need to understand the behavior of all these rocks, basically to model them. Let me remind you, core sampling is extremely expensive. And in this case, collecting the core samples was even more difficult because the rocks are very fragile. And essentially, they did everything to get the core sample, but in the end, they were just retrieving drilling cuttings. In general, there were a lot of problems with it. And every day Google sends me a selection of articles based on keywords, and I see that one. Well, a very important person from a very large company whose office is located on Srednevekovoi Boulevard gave a presentation on this topic at a recent major forum of top oil industry professionals. Well, I see that my solution fits perfectly. But to call such a person and say, hello, I'm Sasha Kirilenko, and I have a solution for you, well, I'm afraid not. I'm afraid that's impossible. But it turns out you can write him a letter. Not to his personal email, of course, but to actually bring a real paper letter to the Special Correspondence Department, right there in the office on Sredinsky Boulevard. Make a mistake and barge in through the main entrance, only to get a reprimand from the security guards. Well, in general, it was a long and amusing story. But the point is, I made the offer, went above and beyond, and then, for 3 or 4 weeks, basically, well, I forgot about it. Well, I did everything I could. Great. And then an official response comes from this person. Well, honestly, it is something truly incredible. Because it is simply such a bizarre and unexpected turn of events, and the mere fact that such individuals are the ones who can make critical decisions, including those regarding funding. It is unlikely that we will ever actually see the day when we are finally allowed to implement a new technology, especially one that is still so very little known. Even now, when it comes to core flow analysis, it's mostly enthusiasts, and only the very top cutting-edge companies talking about it, those that it's no longer extraction for the sake of extraction, but extraction for the sake of efficiency, for digitalization, all those beautiful words. Let's put ourselves in the shoes of someone working down there, someone who actually handles the core, the cuttings, and processes the data right there at the field. He's cold, he's dirty, and he hasn't had enough sleep. And telling him that life could be easier, that you could save a ton of time and money? Well, no, that's not how it works. Just please don't get in the way of his work, and he keeps working. And he's not going to make the decision to push this forward. This is one of those cases where the technology requires, first of all, significant capital investment, secondly, serious consideration, and thirdly, learning about the technology and understanding that it is actually profitable and will make a very important person even more important and even wealthier. But that's exactly what needs to be explained to this person. So this is one of those cases when we discussed in the previous podcast that you need to talk about equipment with those who will be the executors and those who work at the lower levels. This is absolutely true in cases where the technology is already known and well established. And for any of these topics, you can find tons of information on the internet and discuss it with someone at the grassroots level. Yes, and the cost of this implementation might be high, it might even be wasted, but it's not critical. But we're talking about an entirely new technology, about which nothing is known. Something like that can only be introduced from the top down, and mainly, well, primarily through economic justification.
The primary objective of our podcast is to enable this specific kind of real-time synchronous communication, so that our target audience, hopefully, whenever they find some free time and it is convenient for them, can watch our podcast, learn more about our innovative solutions, about our overall readiness, and how we tackle such complex, unconventional tasks. Alexander, yes, thank you so much for providing such an interesting coverage of what I firmly believe are very important issues. Geophysicist specializing in cuttings analysis. I hope this will help and be useful to our viewers. And we would be absolutely delighted to read through and listen to all of our viewers' comments and questions on this topic. as well as your personal thoughts and unique opinions on how relevant and promising you think this truly is. This is our primary target audience and community who may be watching this podcast right now. Alexander, I would probably like to wrap up and draw a line under everything, to briefly summarize once again.
Point 1. Cuttings are something that, if there is drilling, there are cuttings. And it's our decision what to do with them. Either we use them or we don't. That's the first point. Second point. Having information is always better than not having it. And the third point. Having information is always better than not having it, especially when the information comes in immediately, in real time. This translates to significant cost savings, faster decision making, and at the very least, it's quite impressive. So, the topic is very hot and highly relevant. The more people take a genuine interest in it, the better it will ultimately be for everyone, for us as manufacturers of this or related equipment, and for those involved in drilling, like those specific companies that want to get the most efficiency out of their significant business investments. So you could say that right now, you are witnessing the beginning. Maybe even a new revolution in this field, of course.
Let's hope, yes, that this is a revolution in the best sense of the word. One that will bring new results, new tools, and make it possible to increase the efficiency of geological exploration, reduce costs, and enable more informed management decisions.
And maybe, just maybe, the tough life of drillers will get a bit easier. Those guys really have it tough out there.
Let's hope so. Thank you, Alexander.